Okay, so welcome to the today's session of the Seminar of Statistics, Siesta. Today our speaker is Professor Ardo van den Hout, and Ardo received his PhD at the Department of Methodology and Statistics at the Faculty of Social Science at the University of Utrecht. Then he joined the prestigious Medical Research Council Biostatistical Unit in the United Kingdom. This is one of the largest group of biostatistics in Europe. And then he moved to the University College London since 2012. He is a professor at the University College London, and we give him a warm welcome for accepting to participate to this seminar, giving a talk in continuous time state space model. Thank you, Ardo. Your word.
Okay, thanks. Thank you, Marco, for that introduction, and thank you for the invite and organizing this. Also to you, Alejandra, I much appreciate that. So what I will do is I will share my screen. So I've got the slide prepared. So I will do that right now. Okay, so here we go. So I assume you can see my slides. So yes, so thanks. I will talk about continuous time multi-state models. It will be a kind of introduction to this this way of statistical modeling. I will skip some of the more technical details. I will focus a little bit more on applications. Feel free to interrupt me at any time if you have any questions. I also prepared some breaks within the presentation to ask explicitly for questions. So feel free to do that. I hope we can have a bit of a conversation along with the slides. And I guess that's it as an introduction. So let's start. So here on the slide, you can see what I would like to discuss. I would like to start with a general introduction to this type of modeling, multi-state modeling. And then I've got two examples. One is about estimating life expectancies. And the second one is about modeling employment history. And then I will conclude. Okay. All right, hang on, give me a second. Yeah, here we go. So as an introduction, so one way to introduce multi-state modeling is to start with survival analysis. I think most of you will kind of know what that is, right? Here at the bottom of the slide, you see kind of standard survival analysis depicted as a two-state model, right? In survival analysis, we are interested in modeling an event time, and typically the event time is something like alive to death, or maybe disease to healthy, right? There's one time of event of interest, and we model that using a standard survival model. And the idea of multi-state modeling is to kind of extend this approach to more than two states and more than one event time. So here you see a kind of standard example of a multi-state model, which is called the illness-death model. And instead of two states, we've got three, and instead of one event time, we've got actually three event times, right? So here the event times are the transition times between the states. And I will talk a little bit about this three-state model, but you can imagine that you can have also, for instance, a fourth state, right? Or even more states. So the idea here is that, for instance, you have state one is healthy, state two is diseased, and state three is death, right? And we have this process between the states, right? Individuals move between the states, and we may want to investigate this process, investigate which, for instance, which factor contribute to moving through the states. And we may also want to predict this process for individuals who are not in the data. Now, one reason to do it like this is that death is often a competing risk that you cannot ignore. So my standard example here, why you want to take, for instance, death into account when you study certain diseases is as follows. Let's say state 2 is the state where people are demented, so the dementia state, right? So it's typically a disease for the older population, and today you want to investigate risk factors for dementia, right? Now, if you would ignore death and you would, for instance, have smoking as a risk factor, you may see that actually people who smoke a lot will not get demented, right? But that's only because smoking kills them before they are at risk of dementia, right? So if you want to have the full picture of smoking and dementia, you cannot ignore death, right? So this is kind of standard example why you have to take into account death for a disease like dementia, all right? Now, multi-state models can have many forms. So this is a so-called competing risk model. So maybe you're interested in, for instance, competing death causes, right? Maybe you're interested in death by cancer compared to death from other causes, right? And then you would have state 1 is alive and state 2 and 3 are specific death causes. This is used quite a lot in medical statistics. So I am working in biostatistics, but my message for today is also a little bit that this kind of approach can also be used in many other areas. And here I've got 2 examples from my own work with respect to the labor market. So at the top, we see a 3-state model where people move between working and not working, both back and forth. And retired is a kind of absorbing state, right? Very similar to the death state before. But this is one possible application. The second one at the bottom is actually the example that I'm going to discuss today. It's a model for employment history. So here we are interested in people moving from one job to the other job, taking into account maybe some jobless spells between jobs, right? So people might get unemployed between switching jobs, right? So for instance, if you want to see kind of risk factors of moving through this process, right? Going to the next job, then you can investigate that with a multi-state model, right? You can investigate the effect of age, for instance, of gender, of education, etc. All right, so here we've got some examples which show that this kind of modeling is not restricted to biostatistics in general. Now, that is one way to look at multi-state modeling. The other way into this kind of field is to think about Markov models, right? So multi-state survival models, multi-state models in general, can also be defined as continuous time stochastic processes, right? And I guess some of you will have studied Markov models, right? So in our undergraduate study in statistics at UCL, we actually have a course on Markov models. And a Markov model is a stochastic process and it can be in continuous time, and will describe a process like the one on the slide where you have 3 states, okay? It comes with certain assumptions, right? The Markov assumption is explicitly here is the future is only determined by the current state, right? So if I am in state 2, it doesn't matter when I entered this state, my risk of moving towards state 3 is completely determined by the fact that I am in state 2 now. That's a Markov assumption. Now, the way it works with these stochastic processes is that you define this Markov model using a so-called generator matrix. And in that generator matrix, you've got so-called intensities, which you can also see as hazards, right? As the risks of moving between the states, right? So here we have 3 risks of interest. You can move from 1 to 2, that's Q1, 2, Q1, 3, and Q2, 3, right? The entries on the diagonal are just the minus the sum of the off-diagonal, the entries. And the third line is for the death state is an absorbing state, right? So you can't move out of that state. Now, a lot of theory on stochastic processes is about long-term behavior of Markov chains, which can be quite complex. But in our case, when we have an absorbing death state, it's relatively easy, right? We know where it ends, right? We know we end up in state 3. So in terms of long-term behavior, that is relatively simple, right? So that helps if you have an absorbing state. All right. So that's an entry into multi-state modeling from the field of stochastic processes. All right. Now I know that there will be some people who are economists among you, and I'm not one of those, right? Nevertheless, I had a quick look online about applications in economics and finance. I want to be a bit careful here, right? This is not my expertise, but I know that, for instance, Markov models are often used in time series, right? So here the first bullet point, did online search. There are some topics which are investigated using Markov models. Okay. The second bullet point, I should know a little bit more about that because I'm actually one of the co-authors in the second reference there. This is about economic evaluation of healthcare interventions. So this is about having a multi-state model where you are interested in costs with respect to staying in a certain state, right? So this is about time spent, for instance, in a disease state and how that works out in terms of healthcare costs and how it can work out in terms of when there's an intervention, right? And this is linked to my first example where I estimate life expectancy, which is basically an estimation of time spent in state, right? So if you contribute costs to being in a certain state, you have this kind of economic evaluation of healthcare interventions. And you can come up with other examples, right? Currently, I've got an undergraduate student project where we have states defined by the size of company, right? And we investigate factors that are associated by growth of companies, right? And basically moving from one state to another state. Okay, so far for the examples. Now, it's important to realize that the way I work is I always use longitudinal data to kind of estimate my model parameters, right? So I've got the repeated observations within the sample units. And I assume, of course, that the process takes place in continuous time. Now, if you have that assumption that it takes place in continuous time, you can have two types of data, right? You can have knowledge about exactly when someone moves into a state. I call that exact time data, right? For instance, for death, we often have the exact time of death. But you can also have a situation where you only know that people moved into a state within a certain time interval, right? So dementia is an example of that, right? You don't actually see people moving in a dementia state. You will see people every year or so, and at some point you think, okay, this person has moved into the dementia state in the last year. And that is interval sensor data, right? Sometimes also called panel data. So what I want to do is, of course, have a general approach where I allow for all these kind of types, right? So I want to deal with mixed observation schemes, right? Maybe interval sensor data for health states and exact death types. Also, in practice, of course, you will often have irregular follow-up times, right? And you may have right censoring at the end of follow-up. Right censoring is similar to right censoring in survival analysis. If you know that someone hasn't died, you want to use that information, right? I want to say, however, a little bit more about the interval censoring because that's a bit more tricky in this context. And this is an example with respect to medical statistics. Let's go back to that three-state model. And let's say we have time interval T1 and T2, and we observe in this time interval at the start that this person is state 1, and at the end he's in state 3. Right? At T2, the person is state 3. So the underlying trajectory, right, can be two things, right? This person can have moved from 1 to 2 and then to 3, or move directly from 1 to 3. Right? And we should take that into account in our analysis, that those two options are possible. Right? So that is the interval censoring. It basically means that if there are multiple underlying trajectories, you do not know where people are between observation times. Right? And that underlies the second bullet point. Right? So interval sensor data only provides snapshots. Right? If there are more than one possible underlying trajectories of states, then we do not know where the process is between observation times. All right. And this, I mention this because this is part of the reason, this is part of the justification of how we build our likelihood function. All right. Are there any questions at this point, or are there other maybe questions about possible applications? I'm happy to take some questions right now.
Hi. I might have some questions right now. So one quick question is how, if there is any relationship between these kind of models and these the epidemiological models that are in very are very used now, like exposed, like for the COVID pandemic situation. That will be one thing. And the other is so this multi-state process is playing the role of is your your response variable, is whatever you want to study. Is that correct? I mean, you always observe this, but apart from this interval sensor, it's not like I'm trying to relate into hidden Markov models, where these states are hidden, I guess. And I'm not an expert on HMMs, but I'm guessing. So that would be these two things.
I see. Yeah, to start with the last question. Yeah, so the idea is that you observe states at certain observation times, right? So if you have, for instance, you follow individuals every year, you allocate them into a certain state, right? So basically your data consists of states over time. Now, if you have a hidden Markov model, you may have some measurement error in the states. You may observe, for instance, that someone is healthy, but this person might actually be sick, right? So then you have kind of an observed state and a true latent state, and then you get a hidden Markov model. Right? So yeah, that is pretty much the context that we are that I'm discussing here, and I've also looked into this hidden Markov model within this framework. Now, whether these models are used for the current situation with COVID, I do think they are used, but I'm not involved in this work, right? Yeah, I don't have much more to say, but yeah, for sure, these models, these multi-state models, are also used to model epidemics and pandemics. Yeah, but the way I work here is that I need individual data, right? And a lot of models with respect to infection are differently set up. They are used differential equations, right? And they go on a population level. But here I use individual data, so that may be a difference. Okay. Any more questions? All right, thanks. All right, no, thanks for that. Let's move on then. I want to say a little bit more about the statistical modeling before I go into the applications. And I will discuss that just using this three-state model, because everything is more general, right? So what I say for the three-state model can also hold for the four-state model, etc. So what we need to do is we have to model these hazards, right? So the risks or intensities of moving from one state to another state. So in this case, we would have to have three models for three hazards: 1 to 2, 1 to 3, 2 to 3. Right? And this framework, this has been has been out there quite for some time, right? I think the seminal paper here is by Kalbfleisch and Lawless in terms of how you use your data to actually estimate your model parameters. Chris Jackson did a lot of work here, and I also did some work in this area. All right. So what I want to stress is that we model the hazards, and then of course we have to construct the likelihood function so that we can use our data to estimate the parameters for those hazard models. Now here's an example, right? So it's a hazard, so it has to be positive, right? So one way to do that is to have a linear predictor and then take the exponential, right? So the right-hand side of this equation will always be positive. And then we can plug in things that we want to investigate, right? So here, for instance, I've got an example with respect to the modeling of going from state R to state S, right? For instance, there might be an effect of time, right? That's that T. There might be an effect of a covariate like gender. Gender doesn't change over time, so we have a covariate that doesn't change over time. But it might also be that you have a covariate of interest that actually changes over time, right? So here denoted by ZT. So an example would be, for instance, income, right? It will change over time and might still be related to the risk of moving. Now, this times, you have to think a little bit about the time scale in your model, right? So here I've got a couple of examples in the bullet point 2, right? Time can be time since start of this trial, right? If you have a clinical trial. It can also be age in a population study. It can also be calendar year, right? It matters, it will change according to the application. All right, so covariates can be time independent or dependent. It's quite a difference, not so much with respect to fitting the model, but with respect to whether or not you can use the model to use for prediction. And one thing that I just want to mention briefly here is you can add parameter restrictions across transitions. So for each of the transitions in our model, we have a log linear model like this, right? And we can plug in all kinds of covariates. But of course, the number of parameters is increasing quite quickly if you have many transitions, right? So if we have 3 transitions and we've got 4 parameters per transition, we've got 12 parameters, right? So that goes quite quickly up if you add more covariates. So one thing that you can do is to restrict certain effects to be the same across transitions. So here, for instance, in that 3-state model, you could say, well, maybe there's an effect of gender with respect to dying, but maybe that effect is the same for going from state 1 to state 3 as it is for state 2 to state 3. Okay. So it allows you to formulate more parsimonious models. All right, so a little bit more technical now. How do we build our likelihood function? So here's an example of building the contribution for one individual who has J observations. And for the moment, I ignore right censoring. So the basic idea is that this is discrete data, right? So the observations are the states. So we basically, and we condition on the first state. So on the right-hand side of that first equation, we have a multivariate probability mass function, which we condition on the first state, that's y1, on parameter values, all collected in theta, and maybe some covariates, x. Right? And the idea is now to kind of break down this multivariate probability into univariate probabilities that are actually transition probabilities. And that happens when you go from the first equation to the next equation. And you can do that by just using conditioning as a standard operation in mathematics, but also by using the Markov assumption, right? And the Markov assumption states that the future is determined only by the current state. And if you use if you use those 2 things, you can break down this multivariate probability into a series of transition probabilities as indicated on the slide. Right. And this also illustrates why we actually can use our model for this likelihood, because these transition probabilities, we model them with transitions, right? So if we have the risk of the transitions, we can derive transition probabilities, and then we've got the likelihood. Right? That's the idea. That's the main idea. There are adjustments in case of right censoring and exact times, but I will skip those. Now, I said we have a model for the hazards. We need transition probabilities in our likelihoods. So how do we go from the hazards to the likelihoods? Sorry, from the hazards to the transition probabilities. Well, there's just one important equation which you can find in any textbook on stochastic processes, and that is the one which is here on the slide. On the left-hand side, we've got a matrix which has transition probabilities for the time interval T1, T2. And on the right-hand side, we've got a matrix exponential where we have the Q matrix, the generator matrix, defined at T1, at the start of the interval. We multiply that with the length of the interval, T2 minus T1, and then we take the exponential. And this works if the Q doesn't change over time. And as I said, you can find this in any textbook. Now, I want to point out 2 things. First, it's a matrix exponential, which is not the same as a matrix in which you exponentiate the entries, right? So it's an exponential of the whole matrix. And secondly, it only works if the Q doesn't change within that time interval. And of course, typically in our applications, we think that the Q, the risks, the hazards, do change over time. So let's start with that last bit. One way to deal with that is to use some kind of piecewise constant approximation to a Q that changes over time. So let's say we stick to this time interval T1, T2. What we could do is to chop up this time interval into 2 pieces, one which goes from T1 to U, and one that goes from U to T2, right? And then change the Q accordingly, right? So for the first transition probability matrix, we use Q defined at T1. And for the second, we use Q defined midway that interval, right? And then you get a piecewise constant approximation to a Q that changes continuously over time, okay? So this is how I deal with the fact that my Q may change over time, and the fact that I want to use this matrix exponential, okay? Now I want to say a little bit more about this matrix exponential because there are some issues with that. And those issues are nicely illustrated by this title of a paper by Moeller and von Loon. The title is 19 Dubious Ways to Compute the Exponential of a Matrix 25 years later, right? So the title of that paper already illustrates that a matrix exponential is not a trivial thing. Now the matrix exponential itself is just defined as it is here on the slide, which is a standard definition of an exponential, right? But now, of course, we have A being a matrix, and the T here is a scalar. Now, many things are discussed in that paper, and one of the dubious ways to actually do it is to use eigenvalue decomposition. And that is actually what I use, and it doesn't come highly recommended, but to be honest, it serves my purpose. Right? It does work in the applications that I use. I will skip the details here, but I would like to say why I use this eigenvalue decomposition. And that is because I have to maximize the likelihood. And one way to do that is to use a scoring algorithm, right? And if you use a scoring algorithm, if you don't know that, the scoring algorithm will use the first derivative of the likelihood function. And that means that you need the first derivative of a transition probability matrix. And that's difficult because that's a very non-linear function of your model parameters, which you use for the hazards. Right. Now, if you use eigenvalue decomposition, you can tackle this. And this was the basic of this was discussed by Kalfleisch and Loris, right? And you can extend that a bit, which I have done in my work as well. Right. But this is one reason to use the eigenvalue decomposition, because it allows you to program a scoring algorithm. Now, alternatively, you can just use a general purpose optimizer. And this is a very powerful method. It's not very quick, but it's very powerful and relatively easy to implement. So I've often got student projects on multi-state models. And then I'm not going into scoring algorithm, but I say just make sure that you get the likelihood correct, and then just plug it into a general purpose optimizer. Right? So I've been using optim in R, and more recently I've been using this function UC min f in R, which does the job quite well. Okay. All right, so that was a little bit about the technical things. Feel free to ask questions if you have any. But as a summary so far, I hope I've kind of shown that the scope is quite wide, right? Because when I discussed the likelihood function, I didn't discuss the number of states, right? So we can, within this framework, we can vary the number of states. Also, whether or not you go back and forth is not essential to the formulation of the likelihood function. And as I said, we can have a mix of observation schemes, right? We can have interval sensitive data and exact times. It doesn't really matter that much. Now, for some of the models that I use, you can actually use a package in R. It's called MSM. The package, you can ask, there's also software in, for instance, Stata to do this, but I'm more familiar with R. And in that software, you can use a package called MSM. It's very fast. It also allows you to fit hidden Markov models, by the way, where you can model the misclassification, the measurement error actually, and you can model it even by linking it to covariates, right? That's quite a very substantial software there. But of course, it also has some limitations, right? So for instance, if you want to have more elaborate models for the time dependency, you'll probably have to do this yourself. But it can be quite slow, and that is because this matrix exponential, including this matrix, this eigenvalue decomposition, is computationally demanding, right? So it can be quite slow to fit your models. Okay, I would like to discuss my first example. So I've got two examples. The first is about healthy life expectancy, estimating healthy life expectancy. So basically, this is about estimating the time that people spend in the living states. So again, let's talk about this three-state model. State 1 is healthy, state 2 is not so healthy, and state 3 is dead, right? Let's say, given the current age, someone is in state 1. What is the remaining times this person will spend in the states, right? If I would be in state 1, right, I'm 52, what will be my time that I will stay in state 1 being healthy? How much time will I spend in state 2? And of course, that is also about my total life expectancy. That will be the total duration of time I will spend in state 1 or 2. Right? And you can imagine that this is of interest to people who are interested in life expectancies, right? And if we have a multi-state model for this process and it's parametric, we can estimate time spent in state conditional on current age. Okay, so typically we have, for this kind of thing, we have a model that is age dependent, right? Where the risk of moving changes across ages. I want to say a little bit more about this. So this joint work with Fiona Matthews and my student John. We wrote a package actually in R, which is a kind of an add-on to the package MSM. So you can fit a model in MSM, and then you can use our package to estimate the life expectancies. Now, what is a life expectancy? How is that defined? So here you can see that on the slides. So ERS is the the time spent in state S, given that you are in state R at time T, right? So this, for instance, can be, T can be, for instance, age, 53, R can be 1. What will the time be spent in state S, say 2? And that will be this quantity. Now, this quantity is actually an integral, which is on the right-hand side. I don't think this is intuitively clear directly, right? But you can look it up why that is an integral. And the integrand of the integral is a transition probability, right? And notice you integrate over u, so the transition probability is changing with u, okay? Now, if we have a parametric model, we can have transition probabilities for any time, right? So we can have those transition probabilities that make up the integral. The only thing that we have to do is actually do the integration. It's the one-dimensional integration, so that's not so hard. So this is actually done in the package. Now, this is life expectancy conditional on not only time, but also that we know in which state you are, in this case, state R. Often there is also interest in what we call marginal life expectancy. That is time spent in a state irrespectively of where you are now. So this is, for instance, if you want to know, if you take someone from the population, right, and you know his age, but you don't know in which state he is, but you want to know how much time he will be, for instance, spending in state 2. So this marginal marginal life expectancy denoted here by E dot S, right? And it's an expression which has the previous life expectancy and this marginal distribution for being in state R at a certain age, right? It's a kind of prevalence of the states. Now, because we fitted a transition model, our transition model does not include information about the prevalence of actually being in a state given an age. So we have to estimate that, and that's also what the package does, right? So we fit a multinomial logistic regression model to get that marginal distribution for being in a certain state at a certain age. So actually, that's not very complicated to do, but it's nice to have it all in one package. Now, of course, a bit of a warning here, even though it might be relatively easy to estimate life expectancy, it will often be based on extrapolation beyond the data range, beyond the age range in the data, right? So it's not without danger, right? You really have to trust your modeling in order to trust your life expectancies. And yeah, we did some work here. I did this actually with Graciela Muniz, right, who is also here today. We did some work in the EALSA, which is the integrated analysis of longitudinal study of aging and dementia, right? So there was quite a bit of interest to do this, to estimate life expectancies within these studies. And I think that's actually what I wanted to say about my first example. Are there any questions so far? Happy to take them.
Well, Hardo, just a question. So did you apply, of course, this technique of estimating life expectancy to many population? Is there any, say, success case study that you would like to emphasize more? Some data sets where you really extract relevant information from these?
Yeah. Yes, I have not prepared a numerical example, but we published a work in the journal Demography, where we have demographic application, where we also took into account cohort effects, for instance, and where we also compare our method to another method in order to see whether they were given the same examples, right? And so I would like to refer to that paper, which is, I think, quite accessible. It's published in Demography. If you go to my website, you will see it in the list. You can also send me an email. I'm happy to send you that reference.
Thank you so much. Your comment is very interesting because at present the degree of statistics is try to promoting as much as possible the demography profile. So I think that the undergraduate students that are participating today and myself will look as soon as possible to the paper you mentioned. Thank you.
Okay. All right. You're welcome. All right. Let's move on, I guess. Okay. So let's talk about the second example, which I specifically chosen for today because it's not about biostatistics. I thought it's a nice way. There's opportunity to talk a little bit about this one. So here we have 11 states, right? And we are interested in modeling the employment history. So as you can see, states 1 up to 6 are defined with respect to whether you are the first job, the second job, etc. And the 6th job is also 6 jobs and higher, right? But it takes into account that you can also be not in a job, right, between job switching, right? So we have states 7 up to 11 to account for that. In total, we have 11 states. It's progressive, it only goes forward. And I want to talk a little bit more about this. A joint work with Wen Yu Tan, who was a student at UC. All right, so as I said here, states are defined with respect to the number of past jobs and intermediate spells without a job, right? The time scale that I use here is time since entry to the labor market, right? As I said before, it's important to define the time scale and to realize what kind of time scale you are using. So I want to be explicit about that. Now, I was interested in 2 things here. I was interested in using a very specific distribution to model time dependency. This is the second bullet point, right? I'm using the so-called generalized gamma distribution. And I was also interested in using a latent class model where I try to investigate whether there is some kind of unobserved heterogeneity with respect to people who move quickly through jobs compared to people who do not move quickly. I call them the movers. Some of the people who like to hop jobs, right? Those are the movers and people who kind of stay put. And I wanted to investigate that using this model. Okay, so I'm using data from a study for which the data are available. It's a bit older. It's a German study, history study. I use a subset which is available in the R package biograph. And it's quite a study which describes quite a long time period. So there may be some cohort effects, right? And I made a graph to illustrate that because there is a cohort effect and I want to take it into account in my analysis. So if you look at that graph, right, on the horizontal line, you've got age at start of the first job, right? And on the vertical line, you've got year at start of first job, right? So for instance, you see that in 1950, we have a bit of a gray area. People are 15 or 16, right? People started very young in the 50s with their job. So for instance, my mother would be one of those, right? She started around that time when she was 16. And of course, we see that with the later years, we also see an increase in the age at start of the first job, right? As you would expect. So whatever we are going to do with this data, we should take into account some kind of cohort effect. Okay. So what we want to do is we want to define these hazard models for all the transitions in our model. There are quite a number of transitions, right? And I want to use this generalized gamma distribution. Now, this generalized gamma distribution is a bit, in a way, a bit awkward because it doesn't have an explicit expression of the hazard, right? As you may know, if you have a distribution, if you have the hazard, you can derive the density. If you've got the density, you can derive the survival function, etc. You can go back and forth. The relation between the hazards and the density and the survival is on the slide, right? So the Q is the hazard, and you can express a hazard by dividing the density, here denoted by F, by the survival function, here denoted by S, right? You can find this equation in any textbook on survival analysis. I don't think this is intuitively clear right away, but you can work it out and see that this is true. And for this generalized gamma distribution, I had to use this because I do not have an explicit closed form expression for the hazard, right? So I had to do this. But of course, that was also of interest. So I've got a little bit more complex expression for the hazard, but the general idea is it's the same. I model the hazards. From the hazard, I can go to transition probabilities. I use transition probabilities in my likelihood function. I maximize it. I get my model parameters. All right. I use this gamma distribution not for all transitions, but only for a subset. Okay. The gamma distribution, this generalized gamma distribution, is interesting because it includes a couple of well-known other distributions like the exponential, the Weibull, the log normal, and the gamma distribution, right? So it's quite a flexible tool. The gamma distribution, you have specified location parameters and shape and scale parameters. And what I do here is I regress to location parameters, those are the mu's, on covariates, right? So here I plug in the cohort effects. I've got dummy variables for the 3 cohorts, and I've got also gender there and education, only dummy variables, right? So the modeling is quite simple for now. Okay, so that's the basic idea of a fixed effect model here. I model the hazards using some of them. I use the gamma distribution, and for that I model the location parameters with covariates. Now this is a fixed effect model, right? So very much in the framework that I've been talking so far. Now what about this latent class model? So here I want to capture some unknown, unobserved heterogeneity in terms of people who move quickly and people who move slowly. So what I did is I defined 2 latent classes, and for each class gets its own parameters for moving between the states, right? It's just that I don't know which of the individuals in the data belong to which class, right? So the class membership is latent. And I impose certain parameter restrictions so that I can interpret my latent classes as mover-stayer classes, right? So that basically means here the second bullet point, I assume the class effects are the same for the first 4 job changes. So that's from going from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. All right, so I've got a bit of a restriction there in terms of the class effect of these latent classes. And I can estimate it, right? So I can actually estimate the probability of being in a certain class. Right here on the slide, you can see that I estimated the probability for individuals to be a mover. I estimated that to be almost 30%. And then I can fit the model, right? Which I did. So I will skip again some of the details here. But if I look at the inference, I see more or less what I would expect to see, right? So that's nice to see. First, if I see that the younger cohorts have higher hazards for all transitions. By younger cohorts, I mean, of course, cohorts in later years, right? You see that they change jobs more often. We also see that men are more likely to move to a new job and also more likely to move from no job to the next job. And also, as expected, right, women are more likely to move to the no job state, right? Some of this data is quite old, and it's kind of, you see what we kind of know from history, right, especially in the 50s and the 70s, that women were likely to exit the labor market due to marriage or pregnancy, right? So you can see that, you notice that you pick that up from the data. And actually that is more or less everything I wanted to say about the modeling here, right? So it's a very general presentation without parameter estimates. But one thing that I would like to discuss is a question that may pop up is, does this model actually describe the data, right? We've got one slide of that. And this is the way I kind of check whether my model describes the data well. You have to think a little bit about what you're going to compare. But here what I did, you can compare more than one thing, right? But here I compare what I see, the survival in certain states. Sorry, the model-based survival, and I compare that with the survival described by a Kaplan-Meier estimate, which is a non-parametric data summary. So if you look at this first slide, on the vertical axis, it says survival in states prior to state 2. So the states prior to state 2 is being in your first job or being without a job after your first job, right? So I compare the probability of being in those 2 states, model-based, so I estimate the transition probabilities, and I compare that with the Kaplan-Meier estimate for that outcome, right? And I do the same for the other states, right? I also do it for survival in states prior to state 3, prior to state 4, 5, and 6, right? And every time I compare that with the non-Kaplan-Meier estimate. And you see that there's quite a good agreement, right? You see a bit of a discrepancy at the end, which is partly due to the fact that we don't have a lot of data, so the Kaplan-Meier estimate is not really working, but also there might be a bit of mismatch in later months, right? But I was quite, in general, I was quite happy actually to see this agreement between the model-based survival in the states and the non-parametric estimates described by the Kaplan-Meier. All right, so this is my last slides. So to conclude, I kind of hope that I showed that multi-state modeling is a flexible tool for the analysis of longitudinal data. Especially medical statistics is very useful if that is a competing risk. But in all applications, I think it's quite an intuitive way of assessing change, especially if there are kind of multiple directions of change, right, which are not nicely nested, right? So I think that works quite well. Of course, there are some disadvantages. For instance, you have to kind of describe your process of interest in stages, right? That's one. Also, the Markov assumption is quite a strong assumption, of course. Even though I want to mention that, of course, when we add covariates and also a time scale, we have more than just the Markov assumption, right? The Markov assumption is conditional on the covariates. So that will help a little bit with that strong assumption. It's flexible, right? We can deal with irregular follow-up times, info sensing, and also missing data. And in terms of methodology, it's a nice, elegant combination, I think, of survival analysis and stochastic processes. Okay, that's it, actually. So happy to take any questions, if there are any.
So can I ask a question, Ardo?
Yeah, go ahead.
So, so in your last example with the job, I don't know, employment history, you said that you had your 2 classes, and then you had an assumption. Can you go back one slide or one, that one? Yeah. So you defined, but for the first 4 direct job changes, was that an assumption that you had to impose because of the data, or why did you choose that assumption?
To be honest, it's a while ago. I don't know exactly my history of coming to this model. But the idea here is that the movers are defined by moving quickly through all the states, right? So that is why I have, it's like a random effect, which I add to the hazard models, and that random effect is shared across transitions. And that makes this definition of being a mover. So if it's high, someone moves quickly through all those transitions. If you do it separately, you lose this interpretation, because someone can have a high intercept for moving from 1 to 2, but then a high random effect for moving 1 to 2, but a low one for moving from 2 to 3, right? And then you would not classify that as a mover. Does that answer your question?
Yeah, no, that was partly my question. It's like, what happens with, like, yeah, you could have different possibilities moving across the state, so I wasn't very clear about that. And can I ask another question about this same example?
Sure.
So if you were going, if you implement something like this, is it possible to think of covariates having different effects across the 2 classes, for instance?
Yes, you can have class-specific effects, and I think some of that is in this model, right? So the thing that you have to do in one for sure is to have class-specific intercepts, right? But you can have also class-specific effects of, for instance, of gender, right? So that's within one class, the effect of gender is different.
But different. So yes, but it's different between the classes or across the different transitions.
Well, the modeling is flexible. You can do both. You have to be a bit careful. It still has to be identified, right?
Yeah.
But in essence, you see, if you look into latent class literature, you see that they do this type of thing, that they have different class-specific effects. And now we have also different transitions, so we can play around a little bit with the options here.
Super. Great. Thank you. Is this a large data set?
I think there are about 600 individuals.
How many, sorry?
600 individuals in that data set. It's a subsample from the study.
Yeah.
Pablo? Sí.
I have a comment and a question. Let me formulate the comment because that would lead to the question. In a previous resurrection, I'm a biologist, ecologist, and we, in ecology in certain areas, we use multi-state models, Markov-based multi-state models to model behavioral changes of individuals over time. We have a longitudinal data sets, and we also include the probability of non-observation, because not every individual is observed in its state at every sampling time. In the type of data that we have in ecology, observations come once a year. So the time scale of transitions is one year. So we estimate probabilities over a yearly time scale. This is the comment, and there are software and all that. But I wanted to know, in your second and last example of the changes between jobs and the time spent between jobs, what was the time scales at which observations or measurements were obtained in your data sets? Are these unequal time transitions or equal time transitions, and how would you deal with that?
Okay,
thank you.
So it's a continuous time model, and also the data were in continuous time. I think it's most monthly, right? But it's not the case that it's, for instance, always the same time interval between observations, right? So it varies across individuals and within individuals. If it would be the same interval for all the observations, right, the same time interval for all observations, then you could also fit a discrete time model. But I would like to, in this case, right, because I have so much variation of the length of the intervals in the data, it makes sense to fit a continuous time model. Does that answer your question?
Yes, it does. Thank you.
I want to ask something, but I don't have the hand. Okay, first, I want to thank you, Ardo. when he started to talk, because my connection falls down. So now I want to thank him to be here and to give us this talk. And I wanted to ask about the last thing that this latent class model, and because I'm confused if maybe it's two type of models or two type of things that you could do with this multi-state, the latent class and the hidden Markov model, because maybe it's the same, or if I'm confused, one thing, the hidden Markov is that you don't observe the real variable, the real dependent variable. And the other thing, this last thing you talk about, is latent class model is you suppose that the sample units are in groups, and you don't observe these groups and I want to, if you could explain more, because I'm confusing these two things. Thank you.
All right. So your characterization of the latent class model is correct, right? So we assume that there are latent groups, right? We don't know which group individuals in the data belong, but we take this into account in the model. So I think that's the way you said that. That's clear. That's clear to me. The hidden Markov model, I think maybe we could talk about two situations. One, you have a hidden Markov model if you have some kind of measurement error in your observation of the state, right? So you see this sometimes in medical statistics where people are screened for a disease and you want to allow that the screening may not give the correct answer, right? So then you want to have some kind of model for the measurement error, and the measurement error here would be misclassification, right? So you would classify someone into a healthy state where actually is a disease, right? So that would be also called a hidden Markov model. So you have a model for the true states, and on top of that, you've got a model for the measurement error, as it were. So that's one application of a hidden Markov model, and it's different from a latent class model, right? Because this is really about the states where people in and the measurement error of that. Another option for latent models, hidden Markov models, is to have an observed process in some kind of continuous scale, and assume that there is a hidden process in states that explains that observed process, right? So then you don't have observations of state, you have observations, for instance, on a continuous scale, and you assume that behind that observation on a continuous scale, there is some kind of state process going on. So this is often used in time series where you, for instance, have the stock market going up and down, right? Kind of continuous way. And then maybe there will be a drop in the economy, right? And then it goes to a low activity state, and it may go to a higher activity state. And this is sometimes used in time series where you assume that there is a hidden state process behind the observed time series. All right.
I understand. Thank you.
Yeah. All right. You're welcome.
I have a question. Hi, Ardo. Thanks. That was a very interesting presentation. So if I understood correctly, you said that you wanted to use this generalized gamma to model this employment data, the second example. But I'm curious about the motivation. Is it something related to the fit to this data or something more general you're trying to probe here?
Right. So my interest was more methodologically, in the sense that I was interested in this flexible distribution, and I wanted to be able to put this into multi-state modeling. And in this case, so what I often use for time dependency is either a Weibull distribution or a so-called compact distribution, right? So that are distributions where you have hazards changing over time. And I was wondering how this generalized gamma distribution would perform compared to those distributions. And of course, in the paper, there's a paper out on this. I compare several models, and I noticed that in some cases, the generalized gamma distribution outperforms the other standard distributions that I use. So that was a reason for me to investigate this and also to get help to get it published, right? But there was not something in itself in the application that I thought, oh, this should be a generalized gamma distribution, right? That was
but it offers a better fit with some data.
Yes. In
this
case it worked better. Yeah.
Right. Thank you.
You're welcome.
Please, more comments, more questions? Ardo, one question more. A crucial point, say, in the class of models that you presented is the transition function, which you assumed, say, time inhomogeneous, right? So what are the main, say, suggestions that you may give us regarding the estimation of this time varying transition function?
Right. Okay, so what I normally do myself is I always start with the exponential, so without any time dependence, right? I always start with the most simple model with one intercept basically for each transition, right? Because that typically fits well, and that's where I start my estimation. And then I often use actually the MSM package where you can fit more or less a complex distribution. So you add basically, I'll show that to you in the slides very quickly. So, sorry. So this this dependence of the time in this equation actually is a complex distribution, right? So this psi here is one parameter of the complex distribution, right? So you have a complex distribution can be defined by an intercept and an effect of time exactly in this way. And because you can fit this model in MSM, it gives you quite quickly an idea of the time dependency. And then you may want to investigate other time-dependent models like the Weibull or the one that I presented. The only thing, there's a catch here, the only thing that you have to be very careful with is this time dependency and this piecewise constant approximation, right? So I can only use the matrix exponential if I assume that within a time interval, the generated matrix doesn't change, right? And if I got long time intervals in my data, I may have to do something ad hoc to kind of chop that long time interval up into smaller pieces so that the approximation works better, right? So that's a bit of a tricky thing. You have to think a little bit about that. If there's time dependency in your model, if you've got relatively long time intervals in your data, and by long, I mean long relatively to the volatility of the process itself, then you have to be a bit careful with actually fitting the models, right?
Yes.
So,
sure. Are you saying or suggesting, if I understand, that we may fit the model, say, for several period of times? I mean,
yes.
I see. And then join the estimation together in some sense.
No, what I actually mean is that sometimes if you have long time intervals in your data, you might actually want to add some records in your data with intermediate states. If you know where people are, adding those records will improve the piecewise constant approximation because you make your time intervals between your observations smaller.
I see.
Right, so you can sometimes augment your data in order to get a better approximation.
Yes. And I mean, is it also relevant how much the estimation of the transition density may vary if according to the choice of ecovariates or the level of ecovariates? I mean, I assume there is all a process in order to include in the specification of your transition density, despite the available data, some covariates, some levels of covariates, I mean, sort of variable selection, I mean.
Yes. Well, in principle, you can actually, everything that you do for linear models, you can actually also do within this context. The only problem is that you may run quite quickly into numerical problems when you fit the model. So this matrix exponential is a bit of a tricky thing. And if you have, for instance, if you look here on the slide, if for instance, your x variable can have high values, right? And it takes exponential of a high value, your hashes can actually be quite large. And that can give numerical problems. So even though in theory you can add any covariates that you like, you have to be a bit careful, both with the number of covariates, but also with the scale. So you may want to, for instance, center the values of your covariates or maybe transform. So for instance, if you have H in your model as a covariate, I typically center H because else I might run into numerical problems. There's a bit of a trial and error there in terms of adding covariates. That's one reason why I always start with the exponential, right? And I add the covariates one by one.
Okay. Thank you, Ardo. Thank you. Is there more comments, questions? Okay. Well, I forgot to mention at the beginning that Ardo is the author of a relevant monograph in these topics. You may find the reference of his monograph in his webpage, Multi-State Survival Models for Interval Censored Data. This is a monograph which is published with CRC Press, Chapman and all, and it makes explicit mention to interval censored data that today are referred in some sense marginally, but they introduce, I mean, a lot of technical challenges, and we'll be able in the future soon to come to give us a course regarding these relevant topics, as it was scheduled. But pandemic changed the entire plan. If there is no other comments, then we may give Ardo a warm applause and thank you again for his great seminar. So thank you, Ardo.
Thank you.
Thank you. Also, I will take a few seconds more to announce the next seminar. Next Wednesday, el próximo miércoles, vamos a expresarnos. El próximo seminario será a cargo de Francisco Berseche, que nos hablará sobre inferencia ecológica, una aplicación a mapas electorales. Así que están todos, obviamente, más que invitados a participar de esta nueva sesión del seminario el próximo miércoles. Thank you so much, Ardo, for your presentation again. Gracias a todos. Thank you all for your participation.
Okay, you're welcome.
Thank you. Bye.
Thank you very
Thank you.
much. Bye.
Bye. Thank you. Gracias.
Ciao, ciao.
Gracias, chao.
Ciao.
Okay.
Excellent. Great seminar. You kept the level of your talk in such a way that I think most of us have been able to catch the essence. Of course, there are so many technical details and challenges that